Hello everyone, I am Himanshu Mishra and welcome today for week 7 tutorial class of engineering mechanics. So today we will going to discuss about the kinematics in the mechanics kinematics part of the engineering mechanics course, which is basically belongs to the dynamics. So we start with the one friction problem that covered in the last week based on the belt friction. So we will solve one problem belong to the belt friction, and then we will move to the dynamics part where we will start solving questions from the translation regarding how particles translate in the Cartesian as well as in the curvilinear coordinates. So we will begin with a very basic principles that you might have seen in the class, that how to define the velocity, how to define the acceleration, what are the equation for the constant acceleration, and what are how to solve the problem if the acceleration is not constant and instead it is changing, or it it is given in terms as a function of some velocity or some distance, or in any case the acceleration is not constant. So in the first part of the dynamics, we will be solving problems where the acceleration is constant and where the acceleration is not constant at all. So we know that if the acceleration is constant, there are three set of equations that you can use. So at least I will revise those equations. And when the acceleration is not constant, then you actually need to use mathematical concepts like either you need to use the integration to calculate the distance, or you need to take the derivative to calculate the velocity, and so on, that we will see. And then we will move to the curvilinear problems, where we define the problem in the tangential and the normal direction, and we will see how to find the same in those coordinates. And then in the last part we will move to the polar problems. So basically today we will be solving a huge set of problems. So we will begin with a one friction problem that is belongs to the belt friction problem. Then we will solve few constant acceleration problem, and what happens if there is a variable acceleration in the Cartesian coordinates. There are a couple of problems which are actually based on uh, the very basic concepts, like what is the difference between distance and displacement. Like if you have given uh, so if there is a body which is covering uh, some certain distance by turning so many turns, it will cover some certain distance. Then how will you differentiate between distance and displacement? Because in some kinds of problem it is very crucial to distinguish between two. And then in the next problem we will use that concept. So the concept is very easy, and we will use that concept to find the velocity of the particle, and then we will move to the curvilinear coordinates. And in the end we will solve problem by using the polar coordinates. So basically these types of problems, in these types of problems we have to solve for the rotational motion. So in this class we will be first solving the translational motion, and then we will move to the rotational motion where we have to change the coordinate system to either curvilinear or polar coordinate system. So the circular motion actually can be defined by both ways. Either it can be defined by curvilinear geometry, in the curvilinear geometry, or in the polar coordinates, or in the polar geometry. So first we will see a very basic example. It belongs to the friction, which is belt. First let me write down the question. So sample problem. So here, determine the lever force P needed to prevent the wheel from rotating if it is subject stick to torque M equals 250 Newton meter, and the coefficient of static friction between the belt and the wheel is mu s, which is 0.3. So I have here a wheel here. So this is my lever, and here I have a force P, which is the external force we need to find. Let's say this is the center, and here we have a movement which is acting, which is M. The radius of the wheel is 400 millimeter, and this distance is 200 millimeter, and this is 750 millimeter, and this is point A. Okay, so this is the system. So there is a belt drive wrap around this wheel, and we need to find the external force P required to prevent the wheel from rotating. And here the coefficient of friction is given between belt and the wheel is 0.3, and the moment M is given, which is 250 Newton meter. So from the question you might have able to guess that since we require to find this external force P, we need to use the moment balance equation. So you might have already guessed that for the belt friction drive, you can use the equation T2 by T1 equals e to the power mu theta. Here mu is the static coefficient of friction and theta is the angle of spreading of this belt around the wheel. So from the figure you can see the angle is this. This is our angle, which is 3 pi by 2. So theta is 3 pi by 2 because this is the contact length of the belt with the wheel, which is I am showing in the blue color. So here theta is 3 pi by 2. So sorry, this should be 1. So T2 here we need to find out. So I can actually make the free body diagram on the wheel first. So this is my wheel. So let's say this is my force F dash and this is force F. Okay, and this is point A. So if I take the moment along point A, I will have force F multiplied by 200, right? Because the perpendicular distance is 200 millimeter from point A to the force F, plus P is 950 millimeter equals to 0. So these two forces are acting here, and this F dash is actually acting at the point A. So there will be no movement from the force F dash here. So here I can actually find the force, which is F P 950 by 200. So I will get F as 4.75 p. So this is my F. So I already found F. Now I can find F dash from by using this relation. So here T2 is my F dash and T1 is my F. So I will have here F dash by F equals e to the power mu theta. So I can write this as F dash equals F e to the power mu theta. So F dash equals F is 4.75 p e to the power mu theta. So my mu is 0.3 and theta is 3 pi by 2. So I will get F dash equals 4.75 p e to the power 1.413. So this part is 4.108 multiplied by 4.75 p. So on calculation I will have 19.514 p. So this is my F dash. Okay, so earlier we took the movement at point A, which actually lie here. So this is my point A. So when we took the movement at point A, the forces which create the movement is this F and this force P. Now if I take a movement at point B, this point, then I can have a movement due to force F, due to force here F dash, here this F dash, from F and from P. So all three forces will create a movement across point B. So in this way we can actually able to calculate P because we already have calculated F and F dash. And now the third force which create the movement along point B is this force, external force P, which is unknown, and we already know F and F dash. So in this way we can actually able to find what is P. So if I take the moment along point P and summation equated to 0, then I will have F dash multiplied by 0.4. So this is my F dash and this is my perpendicular distance, which is 0.4 meter, which is 400 millimeter, the radius of this wave. Then there is a moment which is there, so it's 250 Newton meter. Then there is a force F, and if it has a perpendicular distance, same perpendicular distance, this 0.4 millimeter from point B. And this should be a negative here. So my F dash is 19.514 p. So it's 19.514 p multiplied by 0.4 plus 250 plus F, and F is, we already found it is 4.75. So on calculation, I will get force PS 42.33 Newton. So just to recap here, we solved one of the example problem where we have given the wheel and there's a belt drive which wrap around the wheel, and there's a lever which is connected, and at the end of the lever there is an external force P which is acting, and that we have to find. So what we did, first we use the moment equilibrium equation at point A to find the relation F in terms of P. Okay, then we actually use the equation for the belt drive where the ratio of the forces equals c to the power mu theta. So theta is the angle making by the belt when it is wrapped around the wheel, and mu is the static coefficient of friction. So by using this formula, we actually can able to define the relation between F dash and P. Then we take the moment along B, because if we take the moment along B, the moment will caused by F dash, F and P. So we already found F dash and F in terms of P, but P is the unknown quantity. So we can easily find P, because if we take the moment along point B, the only unknown force is P. Rest F dash and F is the known forces. So then by using this equation, we can actually able to find the unknown force. So that's it for the friction. So now we will move to the dynamics part of the engineering mechanics. So before moving to the problems, let's revise some of the basic equations. So we know that the velocity can be defined as the change in the displacement with time. So if my v is the velocity, then it can be defined as ds by dt. So here s is my displacement and t is my time, right? So similarly, the acceleration can be defined as change in velocity in time, change of velocity in time. So it will be defined as acceleration dv by dt. So let's say my acceleration is constant, then I can use these two equations to define some expression which is valid only for the constant acceleration. So for example, if I use this relation, I will have, I can write like dv equals a dt. Now if I integrate, let's say from v0 to b and here from 0 to t, then I will get v minus v0 equals, now my acceleration is constant, it will not change in time or space, so it will be outside of integral. So I can write this as a t. So this is one of the equation which is valid when the acceleration is constant. And now you can easily see in this integral equation. For example, let's say my acceleration is function of time, it is not constant but it is changing with time, then you cannot actually shift this acceleration outside here. You need to consider this acceleration inside the integral, and you will not get this reaction then. Right? Similarly, let's say we have defined the velocity as the rate of change of displacement in time. So I can write the displacement as ds v dt, and I can integrate it from s0 to s, and here from 0 to t. If I substitute this expression here, I will have this expression. So this is the expression we need to integrate. So here v0 is a constant, so we can pull out from the integral, but this term is not. So here we can only pull out acceleration because the acceleration is constant, but we need to integrate with respect to time here. So I can split this integral as v0 0 to t dt plus a, which is outside, t dt. So if I integrate this, so this will become s minus s0, and this will be v0 t plus a t square by 2. So my s will be s0 plus v0 t plus a t square by 2. And you can see you will get another equation which is valid only for the constant acceleration. Now you can actually derive one more equation by using these two expressions. So here this expression you can write as dt equals ds by v, and this expression you can write as dt equals dv by a. So you know this and this actually save the small change in the time, so I can equate this equation together. So it will be ds by v equals dv by a. So this I can write as, if I simplify this, I can write this expression as v dv equals a ds, and I can integrate this as from v1 to v2 and s1 to s2, and if I integrate this I will get v square by 2 from v1 to v2, and here a is a constant, acceleration is constant, so I will pull acceleration out from the integrand, so I will have s2 minus s1. So this will be v2 square minus v1 square by 2 a s2 minus s1. I can multiply 2 here. So this is my third equation. So we got the three equations which actually define the relationship between the velocity, displacement and acceleration when the acceleration is constant. So you can even find the acceleration from these equations, but that will be a constant and will not change in time. But what if the acceleration is not constant? Then you cannot simply take this acceleration out of the integral. So you can, when the acceleration is constant, you can solve this as like this. You can actually take the acceleration outside of the integral and you actually arrive at this equation. And similarly, you actually arrive at this equation if you integrate the earlier equation that we have seen here. So all these equations are for the constant acceleration. But if it is not constant, then you have to integrate this whole quantity. You need to integrate this whole quantity here. And there is no general expression for that. You just integrate this whole quantity, and whatever the expression you get, that will be the unknown quantity. That will be either displacement, velocity, or the velocity here. There is no general expression for the variable acceleration. So mostly we will be solving the problems based on the variable acceleration, because for the constant acceleration case, the problems usually are very straightforward. You just need to use either of these, either of the one equation from these three equations. So you just simply use either one of these equation directly to get the answer. So mostly we will try to solve the problem where the acceleration is variable and it's not constant. So we will start from the very easy problem. So the first problem is the velocity of a particle which moves along the x-axis is given by v 2 minus 4t plus 5t to the power 3 by 2, where t is in seconds and v is in meter per second. Evaluate the position s, velocity v and acceleration a when t is 3 seconds. The particle is at position s naught equals 3 meter when t equals 0. So here we have given the expression for velocity, which is 2 minus 4t plus 5t to the power 3 by 2. And we need to find the position s, velocity v and acceleration at time 3 equals 3 seconds. And we have given initial position of particle, which is 3 meter at t equals 0. So this is the initial position. Okay. So we have given the expression for velocity and we need to find the position, velocity and accelerations, which means that we can directly find the velocity because we already have given the expression of velocity. So we can directly find the velocity at time equals 3 seconds. We just need to substitute time here, which is 3 seconds. So we will get the velocity at time equals 3 seconds. So finding the velocity from the velocity, because we have given the velocity expression, so finding the velocity at a specific time is very easy. So it will be velocity at time equal 3 seconds will be 2 minus 4 multiplied by 3 plus 5 multiplied by 3 to the power 3 by 2. So I will get the velocity as 15.98 meter per second. So this is the velocity at time equals 3 seconds, and it is pretty easy because we have given the expression of velocity. So to find the velocity at time t equals 3 seconds, you just need to substitute here the value of time where you need to find the velocity. So it's t equals 3. So we just substituted t equals 3 to find the velocity at the same time. Now to find the position, we will be using the expression that we just saw now. So if the velocity can be defined as ds by dt, we just perform this integral few minutes back. So my position will be, sorry, this is v equals ds, so it will be, position will be v dt, and we are integrating from s naught because we already have given the initial position s naught to s, and here from 0 to time. We already performed this integral before coming to this question to find out the expression for the constant acceleration. So on integrating this, we will have s minus s naught equals, and the expression of v is 2 minus 4t plus 5 t 3 by 2 dt. So it is s minus s naught, and on we can write this as 2t minus 4t square by 2 plus 5t, and this we will have 5 by 2 and to the power 5 by 2, and s is 3, I guess, yeah, it's 3. So my s minus 3 will be, so we need to find the position at time equals 3 seconds, so we need to substitute here t equals 3, so it will be 2 multiplied by 3, 4, so this will be cancelled, so it will be 2, 3 square plus 5, 3, 5 by 2 divided by 2.5. So this will become 2. So this we need to find. So my s minus 3 will be so my position at time 3 seconds will be 22.17. So at time 0 my position was 3 meter, and at time 3 seconds my position is 22.17 meter, right? So now we need to find now acceleration, and the acceleration we just saw, it's given by rate of change of velocity in time. So basically we have already given the expression for velocity, so we just need to differentiate this expression in time. So when we differentiate the expression, we will have minus 4 plus 15 by 2 t1 by 2. So this is my acceleration expression. So if we want to find the acceleration at time t equals 3 seconds, so we need to substitute time t equals 3 here. So it will be minus 4 plus 15 by 2, 3 to the power 1 by 2. So on solve, we will have acceleration at time t equals 3 is 9 meter per second square. So you can see that this problem we have not used. So just to recap here, uh, in this problem we have given the velocity, which is a function of time, and we need to find the position, velocity and acceleration at time equals 3 seconds. So before this question we have actually derived the three expression like this. So we derive actually this equation. So this expression are valid for when the acceleration is constant. But in this question we have not used these equations at all. So, and there is a reason for this, because you can see this acceleration here. The expression of acceleration that we derive is a function of time. So as the time changes, the acceleration is also changes. So acceleration is not constant in this problem, and for this reason we have not used any of these equations. So instead we actually use the general equation that the velocity is given as a change of position with time. Then using this equation we integrate to find the position, which come out as a function of time. Here it come out as a function of time. So then we can actually find the position at any time. So in the question we have been asked to find the position at time t equals 3 seconds, but so you need to substitute t equals 3, but you can find the position at any time. At time t equals 10 seconds, you just need to substitute here t equals 10 seconds to find the position at 10 seconds. Then we use another very general formula that the acceleration can be given as change in velocity in time. So using this expression we actually get the expression of expression, and as we had discussed before that it is not constant and it is a function of time, it is changing with time. So again we differentiate the velocity expression and we substitute the t equals 3 seconds to find the acceleration at a specific time we have been asked for. So you can see that in this expression that acceleration is not constant, and therefore you are using the general equations, this one and this one, to integrate to find the position and differentiate this expression to find the acceleration. So you can also find the velocity from this acceleration in case if you have given some other quantity. So in this question you have given the velocity expression, but based on what you have given you can also use this equation to find the velocity. So you integrate this equation and you might have given some expression of acceleration, so you integrate the expression of acceleration to find the velocity. Here you have already given the velocity, so you differentiate the velocity in time to get the acceleration, right? So when the acceleration is not constant, the procedure is to find the other quantities by using this very general equation. V equals ds by dt and a equals dv by dt. So you have to use these two general relation to find the unknown quantity like s, v and a. But if the acceleration is constant, then you can use these relations. Okay. So this is, here also you can see in the question, a small projectile is fired vertically downward into a fluid medium with an initial velocity of 60 meter per second. Due to the drag resistance of the fluid, the projectile experiences a deceleration a, which is given minus 0.4 v to the power 3 meter per second square, where v is in meter per second. Despite the determine the projectile velocity and position 4 seconds after it is fired. So it's a similar problem, and unlike in the previous case where you actually find the acceleration by a differentiate the velocity expression in time to see that the acceleration is not constant because it is a function of time. Here in the question itself you can see that acceleration is not constant because it's a function of velocity v cube, right? It's a function of velocity v cube and v is changing, v is variable, which means that a is also variable, it's not a constant. So which means that you cannot use these three equations, standard equation. You need to use this general formula to find the unknown quantities. So for that, you are already given the initial velocity, which is 16 meter per second, and you need to find the velocity and position at time 4 seconds. In earlier question it was 3 seconds. We need to find the position, velocity and acceleration at time equal 3 seconds. Now we need to find the two quantities, position and velocity, at 4 seconds. So it's a very similar problem like just we have solved before. So we have already given the acceleration, so we we can make use of this expression. So acceleration is change in velocity in time. So as I said, if the acceleration is not constant, you need to use this general equation to find any unknown. So here you have, so you already have acceleration, but you can find the velocity by integrating. So you can write dv equals a dt, and you can integrate from v0 to v, and here from 0 to t, a dt. So acceleration is not constant, which means you cannot bring this a outside. You cannot do that. So you need to solve this whole quantity. This will be v minus v naught equals 0 to t, and acceleration is given as 0.4 v cube. So wait a minute, I can write this as dv equals minus 0.4 v cube dt. So here I can bring b here, so it will be dv by v cube 0.4 dt. So now I can integrate it from v0 to v, so it will be dv by v cube equals 0 to t 0.4 dt. If I bring this 0.4 here, it's anyways doesn't matter. So I can integrate this to simplify. So I can write this time equals 1 by 0.8, 1 by v square, and v0 is 60. So I'm writing 60 square in place of v0 square. So I can find v0 here. I can find v square here. So it will be 0.8 t 1 by v square minus 1 by 60 square. So it will be 0.8 t plus 1 by 60 square equals 1 by v square. So my v square will be 0.8 t plus 1 by 3600 inverse to the power minus 1, because I am taking the inverse. So my v will be 0.8 t plus 1 by 3600 to the power minus 1 by 2. So this is the expression of v, and we need to find the velocity at time t equals 4 seconds. So if you substitute time t equals 4 seconds, you will get v as 0.55 meter per second. So here it is given the d, you have given the deceleration, which is basically the acceleration but in the negative sense. You can see that the initial velocity was 60 meter per second, but now it reduced to 0.55 meter per second at time t equals 4 seconds. Now you can use another general formula to find the position at time equals 4 seconds, which is the velocity, which is given as the rate of change of position. So to find the position, I can write this as v dt. And you already know what is v, so this is my expression of v, which we found. So this is from 0 to s, and this is from 0 to t, and the expression of v is 0.8 t plus 1 by 3600 to the power minus 0.5 dt. And now you need to take the integral of this equation. Will be 1 by 0.4, 1 by 3600, 0.8 t, 1 by 2 minus So if you substitute here t equals 4 second, you will have s at time t equals 4 second as 4.43 meter. So this is the position at t equals 4 second. So just to recap here, we have given the small projectile which is falling downward, and we have given the initial velocity. And we have also given the acceleration which is actually deceleration expression, and it's a function of v. So we know that it's not a constant, so we cannot use those three pretty famous relations. And we need to find the velocity and position at time equals 4 seconds. So as we discussed, for this case, when the acceleration is not constant, we need to use the general formula. So first we use this formula, acceleration, which can be defined as the change of velocity in time. We integrate the expression here to find the unknown velocity. So we found out the velocity expression, and it is a function of time. So at any time we can actually find the velocity. So we found the velocity at time t equals 4 seconds. Then we use another general formula where the velocity can be given as rate of change of position and time. And to find the position, we again integrate the expression here. And we can write the expression of position as a function of time. So we can find the position at any time, and you can see when you put time equals 4 seconds here, you can actually get the position at the same 4 second, which is 4.43. So it's a very similar problem like a previous one that we have solved. So let's move to the next problem. So here the acceleration of point A is defined by the relation A, which is minus 1.8 sine kt, where A and T are expressed in meter per second square and second respectively, and K is 3. Knowing that x equals 0 and v equals 0.6 meter per second when time equals 0, determine the velocity and position of point A when t equals 0.5 seconds. So it's the same problem that we just have solved. So just like the two problems we have solved, it's a very same problem. So we need to use the same concept. So as you can see here, the acceleration is a function of time. So again, the acceleration is not constant. So you need to use the general equation to find the unknown. So this is what we did in the last two problems. So using the same methodology, you need to find the velocity and position at time t equals 0.5 second. So earlier we find the same at t equals 4 second, and in the first question we found the same. We actually found all three quantity at time equals 3 seconds. So here it is just 0.4 second. So try to solve this problem by yourself because it's the same method that we just have used in the previous couple of problems. So let's move to the next one. So for a short time, the part of the plane in figure is described by y equals 0.001 x square. If the plane is rising with a constant velocity of 10 meter per second, determine the magnitude of velocity and acceleration of the plane when it is y equals 100 meter. Right, so we have given the expression of y, which is 0.001 x square meter, and we need to find the velocity and acceleration when it reach the location y, which is 100 meter. So when y is 100 meter, what is x? Because it will reach some position, and the position always defined in terms of x and y. So we have already given y 100 meter, but what is the position, same position in x? So for this you can use this relation. So when y is 100 meter, then what is your x? So the x you can write as y divided by 0.001. So your x will be y divided by 0.001. So if your y is 100, then your x will be 316.2 meter when you solve this. So you need to find the velocity and acceleration when y equals 100 meter, and at that position your x is 316.2 meter. So basically you need to find the velocity and acceleration at when it reached the point xy, which is 316.2 comma 100 meter. So when the particle reach this location, what is your velocity and acceleration at this point? So this is the question here, and it is given that the plane is rising with a constant velocity of 10 meter per second. So plane is rising at a constant velocity, so it is y component of velocity, which is 10 meter per second. So here the problem is two-dimensional problem, because already you might have figured out, because the point is given in terms of x and y, not alone x and not alone y. It is given in terms of x and y, which means that the problem is two-dimensional, and the vertical velocity we have given 10 meter per second. And we need to find the velocity. So in the two-dimensional case, your overall velocity can be given as vx square plus vy square. And you have already known from the question that what is your Vy, which is 10 meter per second, right? So now you need to find out Vx so that you can actually find the total velocity, right? So but what we have given the expression of y in terms of x. This expression is actually tells you that how the location y changes if the location x is changing. So let's say we will use the whatever we have given in the question. So if I write the expression of Vy, which is the rate of change of y in time, then my Vy will be, my y is 0.001 x square, so it will be 0.001 x square. So now the y and x is a function of time, so I can write Vy as 0.001 multiplied by 2x multiplied by x dot, because this x is a function of time, right? So my Vy is already known quantity, and this x dot, which is x dot is dx by dt, which is basically Vx. So if my Vy is dy by dt, dx by dt is Vx, x component of velocity, right? So this is x dot, which means my Vx is x dot from this below expression, right? Because my change of velocity in y direction can be given as rate of change of y direction. So the velocity in the x direction can be given as rate of change of x direction, dx. So if Vy is dy by dt, then Vx is dx by dt, which is x dot. So my Vy is 0.001 2x Vx. We already know what is Vy. Vy is 10 and it's a constant, 0.001 2x Vx. And we need to find the acceleration and velocity at this position, where x is 316.2 and y is 100 meter. So substitute that here. So we don't need to worry about y here, but here we have x. So if I put x as 316.2 meter, then I can actually find Vx. So my Vx will be 15.822 meter per second. So this is my velocity in the x component of the velocity. Now, as we discussed that if you have given the x and y component of the velocity, the total velocity you can, to find the total velocity you can actually use this relation. So your total velocity will be 15.82 square plus 10 square. On solving you will get V as 18.72 meter per second. So this is the velocity at x comma y equals 316.4 comma 100. So at this position this is the overall velocity, and to find the overall velocity we first find the velocity component Vx, and Vy or we have already given in the question. Right now, another very important thing that we have given in the question is, now the second part, in the second part we need to find the acceleration, which is the total acceleration, and since the acceleration is also a vector quantity we need to find the its component first. So we need to find the x component of acceleration and y component of acceleration, then we can actually find the total acceleration by using this relation. So I was saying that the important thing which is given in the question is the constant velocity at which the plane is rising, which means the Vy is constant and it is 10 meter per second. And the we just define the expression of Vy, which is rate of change of y in time, and Vx is rate of change of x in time. Similarly, my acceleration in y direction will be rate of change of Vy in time, and my Ax will be rate of change of Vx in time. But in the question we have given the rising velocity is constant, Vy is constant, and it's given 10 meter per second, which means its rate of change is 0 because it's constant, it is not changing. So my acceleration Ay is 0, right? So I can use this expression. So my Ay is dVy equals dt, and it is given as, and my Vy is this. This is my Vy which we have found out. Okay. So if I again differentiate this expression to find the Ay, I will have 0.002 x dot Vx, x dot square basically, plus 0.002 x V dot x Ay, and Ay is 0, so basically 0 equals 0.002 Vx square plus 0.002 x Ax. So V dot x is Ax, that we have already discussed here. So now I can find Ax here because we already know what is Vx. We already know at which location we want to find. So we need to find acceleration at x equals 316.2 meter and y equals 100 meter. So at this position we need to find Ax. So we just substitute here. So Vx is 15.82. x is 316.2 ax. So you will get acceleration of minus 0.79 meter per second square. So this is the ax you found, and you know ay is 0, and ax you found is minus 0.79 meter per second. So you can actually find the total acceleration, which is ax square plus ay square. So here ay is 0, which means the total acceleration will be 0.79 meter per second square. So this is the unknown acceleration. So as you can see that this problem is a bit really involved, because you need to know very basic concepts to solve this problem. Just a second. So here, to solve this problem, you need to carefully read the question here because there are a lot of hints which is given in the question. So just to recap here, we have in this question we have given the position y, which is changing using this expression. So as x is changing, y is also changing. Now it is said that the plane is rising with a constant velocity of 10 meter per second, which means your Vy is constant and it is 10 meter per second, and it is a constant. And we need to determine the magnitude of velocity and acceleration at y equals 100 meter. So at y equals 100 meter, we need to find the acceleration and velocity. But it's a two-dimensional problem that you can see it's a Cartesian coordinate x and y. So if y equals 100 meter, so if you have any point where y equals 100 meter, there will be some definite x also associated with that point. So if you substitute y equals 100 meter here, you can actually find x by using this relation, and we found it was 316.2. So basically at this point you need to find the velocity and acceleration. So what we did, we use the known fact which is given in the question, that the velocity is Vy is constant and it is 10 meter per second. So we define the general relation that the Vy is rate of change of y in t, and we put the expression of y here, and x and y are the position of time. Otherwise you will not get any component of acceleration and velocity, because if it is not a position of time, it is depend only on x, then you can, it is independent of time at all. So acceleration and velocity will not vary in time. So as the velocity is changing, acceleration will not change in time due to that velocity. So that's why this position should be in time. So if x is a function of time, you can, if you differentiate this expression, you will get this. So if Vy can be written as y dot, which is dy by dt, then my Vx can be written as x dot, which is the dx by dt. And so this is your Vx, and from this expression of Vy, you actually get the unknown Vx, or the velocity in the x direction, which is 15.82 meter per second. So now you have Vx and Vy. Vy is 10, which is given in the equation, and you just found Vx, which is 15.8, and you can easily calculate the total velocity by this expression. So using the similar expression, you can actually calculate the acceleration, total acceleration, which is given in terms of the component ax and ay square. But in the question, it is given the Vy is constant, the rising velocity is the constant, which means if I write the acceleration as change of velocity in time, it is 0, because my Vy is constant, therefore Vy will not change in time. So this means my acceleration in the y direction is constant. But I can write, but the acceleration in the x direction is not constant. it can be written as dvx by dt. Anyway, we use this expression here again to write down the expression of ay, but ay is 0. So from this expression, we actually can able to recover the unknown acceleration term ax. And once we got the ax, again we can easily find the total acceleration. So you can see the problem is pretty much tricky, but to solve this problem you need to understand the question first. So read the question very carefully and then apply the same concept. So here in this question we apply the same concept. It is just we follow the question more precisely. Each and every statement we actually follow a bit. So let's move to the next problem. So you can see again it's the same problem. So you can solve this problem. So in the first problem that we have solved, we have given the velocity and we have been asked to solve the position, acceleration and velocity. So we use the general formula that we have been using since the beginning of this class to solve the unknown uh, variables. Using the similar concept, we can solve this question. So try to solve this question by yourself. So again you can use the very general formula that the velocity can be given by rate of change of position in time, and the acceleration is rate of change of velocity in time. And the position here again given in a two-dimensional plane, and this is our x component of position and this is the y component of position. And the vector, it's a position vector we have given. So until now we have been dealing with the scalar quantities mostly. So we actually use the expression like v equals dy by dt or ds by dt, and acceleration is dy by dt. So most of these expressions are scalar in nature, but in 2D or in 3D the position actually can be defined by the position vector as well, which is defined in this question. So you can see instead of giving the position, you have been given the position vector. So there will be a two component of position. One is x component and another is the y component, right? So how to find the velocity then? So you have given the position vector, which is 5 cos 2t in the which is the x component, and 4 sine 2t, which is the z component. So the velocity vector can be given as the rate of position vector, which is basically you are differentiating this position vector f cos 2t I 4 sine 2t in the y component. So basically we are differentiating this in respect to time, so it will be 10 minus 10 sine 2t, this is the x component, plus 8 cos 2t, this is the z component. So this will be my velocity vector. So we need to find the acceleration and velocity at time t equals 1 second. So if I put t time equals 1, I will get minus 10 sine 2 plus 8 cos 2 in the y component. So on solving this, I will have minus 9.093 in the x direction and 3.329 in the j direction. So this is my velocity vector at time equal 1 second. So if you want to find the magnitude of velocity, because this is a velocity vector, and in order to find the magnitude, you will use the expression that we have used earlier. that v equals under root v x square plus vy square. So my vx, this is my x component of velocity and this is my y component of velocity. So it will be 9.09 square plus 3.32 square. Then my velocity will be 9.68 meter per second. And in the similar manner, you can actually find the acceleration. So the acceleration vector can be given as rate of change of velocity vector in time. And you already know what is the velocity vector. This is the velocity vector. So again, you have to differentiate it with respect to time. So you will get here minus 20 cos 2t minus 16 sine 2t j. So this is our acceleration vector. So this is our acceleration in the x direction and this is our acceleration in the y direction. And in order to calculate the total acceleration, we will be using this. So our total acceleration will be at time equals 1 second. It will be minus 20 cos 2. 20 cos 2 square plus 16 sine 2 square. So your acceleration will be 16.8 meter per second square. So this is our acceleration. So just to recap, here in this question we have given the position vector. So until now we have been solving the problem in which we have given the position, scalar position. But in this question now we have given the vector position. So we have given the position vector and we need to find the velocity and acceleration. So we use a general formula. So in previously my velocity can be given as rate of change of position in time, but now it will be rate of change of position vector in time. Similarly, my acceleration was given as in the earlier problem, it is a rate of change of velocity in time, but now in this problem it is rate of change of velocity vector in time. So you need to consider the whole vector. So to find the velocity, we use the position vector. We differentiate with respect to time, and at time t equals 1 second, we can able to get position vector. So earlier we used the rate of change of scalar position in time, so we got the velocity, which was the scalar quantity. But now it's a rate of change of position vector in time. So output will be the vector as well. So output will be the velocity vector. So this is the x component of velocity and this is the y component of velocity. Then we use this relation to find the overall magnitude of the velocity. In the similar manner, we define the acceleration as the rate of change of velocity vector in time. So when we differentiate this velocity vector, we actually got the acceleration vector. So this was our x component of acceleration and this is our y component of acceleration, and we use this expression to find the magnitude of acceleration. So this is how we solve if we have given a vector quantity like a position vector in time. Similarly, if you have given the, let's say you have given the here the velocity vector. So previously we have solved a lot of problem where in some problem we have given the velocity expression, in some problem we have given the acceleration equation, but all those quantities there was scalar quantity. But here let's say you have given the velocity vector expression, then you have to use the same expression, but you have to integrate to find the position, but you have to integrate the velocity vector expression. So unlike you were integrating the scalar expression in the earlier problem, now you are actually integrating the vector expression to find the position vector. So output also will be should be a vector quantity. Similarly, to find the acceleration, you can use the same expression, that rate of change of velocity vector in time, to find you will get once you differentiate the velocity vector in time, you will get the acceleration vector. So now we are talking about the vectors. So this problem actually related to a very simple concept, that how to differentiate between the position vector and the distance, or how to differentiate between the displacement, which is a vector quantity, could be a position vector, and the distance, which is a scalar quantity. So the displacement is often written as a vector quantity and the distance is often written as a scalar quantity. So here the question is, the car travels from A to B and then B to C as shown in figure. Determine the magnitude of displacement and distance, right? And let's say if I assign the coordinate, let's say this is x and this is minus x and this is y and this is minus y. We have to assign the coordinates because we need to find the displacement and distance, and displacement here is a vector quantity, and to define any vector quantity you need to first define the coordinate system. So here we define the Cartesian coordinate system. So what is the distance? So distance is a very simple concept, that in the question we have given that car start from position A and it go to position B, then from B it go to position C. So what is the total distance traveled? So first it traveled 2 kilometers, and then from position B to position C it travels 3 kilometers. So the distance is, which is the scalar quantity, it is just additive. It actually satisfies the additive property, which is 2 plus 3 meter. So it is 5 meters. So the distance is 5 meter because it first moved to A to B, which is 2 kilometer, then B to C, which is 3 kilometers. So the overall distance is 5 kilometers. Sorry, it's a kilometer. So it's a 5 kilometer. So this is the distance, but the displacement is the vector quantity. And you can see that first the car travels along the x-axis. So first car travel along the x-axis here, and how much, what is the magnitude it travels along this component, along this x-axis? It is 2 kilometer. Then it travel entirely in the y direction, entirely in one direction, which is y direction, which is 3 kilometers. So the magnitude of the position vector in the y direction is 3 kilometers, right? So magnitude of displacement or position vector in x direction is 2 kilometers, and the same thing in the y direction, magnitude of a position vector or displacement in y direction is 3 kilometers. And you can see that it is going downward. B to C, it is going downward, it is going towards minus y. So my displacement will be plus 2i minus 3j, because first it is moving in plus x direction from point A to point B, it is moving in a plus x direction and the magnitude is 2 kilometer. It is entirely moving in the x component and 0 y component. So it is 2 I cap plus 2 I cap. Then it is entirely moving from B to C here. It is entirely moving in the y direction, actually in the negative y direction. So, and the magnitude is 3 kilometer. So, my displacement vector will be 2i minus 3j. So, this is my displacement or the position vector, and this is my the overall distance, which is a scalar quantity, which is covered by the car. So, for the scalar quantity, you can see that it is it satisfies the additive property, which means that you can just keep adding numbers, total numbers, irrespective of any direction. So whether the car follow this, then it turns, then it again turns, then it again turns, then it again turns, and it keep moving in a zigzag fashion. You just calculate the distance and keep adding the numbers. You will get the total distance traveled. But to define the position vector, you need to consider the direction as well as the magnitude. So first it is moving in the plus x direction. Plus x direction, it has some magnitude x1. Then it is entirely moving in minus y direction with a magnitude y1. So it will be written as plus x1 I minus y j bar. Then it's moving in the minus x direction, let's say x2. So it will be x1 minus x2 I cap, right? Then it is moving again negative y, which is has a magnitude y2. So it's minus y1 minus y2. So this is now your displacement or position vector x1 minus x2, y1 minus y2 until this position, from this A to B position. This is your vector now, x1 minus x2 minus y1 minus y2 j cap. So you can add in the x component, you can add all the x component together and you can add all the y component together here, and you can actually define the vector quantity in x in terms of x component, which is given in terms of I cap, and in terms of a y component, which is given in terms of j cap, right? So this is the basic concept, and this is how we differentiate between the displacement and distance. So we can use this concept to solve one easy problem here. So here a particle travels along the curve A to B in 1 second. If it is take 3 seconds for it to go from A to C, determine the average velocity when it goes from B to C. So in the question it is given that particle take 1 second. It take 1 second to move A to B, and it take 3 seconds to move A to C, which means to travel from B to C it should take 3 minus 1, 2 seconds, right? Which is very obvious, because if it is taking 3 seconds to move from A to C and 1 second to move A to B, which means it should take 2 seconds, right, to move from point B to C. And it's very obvious statement, it's very general statement. Now we need to find the average velocity when it goes from B to C. And to find the average velocity, we need to define the displacement or the position vector. So my average velocity, which is a vector quantity, can be given as displacement, rate of change of displacement in time, and my displacement vector I can given as RAC minus RAC AB divided by delta t, right? So delta t is my 2 seconds here because I need to find the velocity of particle from when it is moving from point B to point C, and we have already given the time from A to C and A to B. So I can write the displacement or the position vector from A to B, and then I can also write the position vector at from A to B. So I can first write the position vector from A to C, and then I can write the position vector at A to B. So you can see the difference of this position vector is basically this position vector BC. So how to define the position vector A to C? And for this we will be using the concept that in the previous question we have defined how to we discussed quite a lot in the previous question that how to define the displacement or the position vector. You can say that this is a 20 meter and this is also 20 meter, right? This is again 20 meter. And to define the position vector or AC, the magnitude here is 40 meter and it is entirely in the x direction because it's a vector quantity. So we discussed that first you need to define the Cartesian coordinate, and the Cartesian coordinate you can see that it is entirely moving in the x direction. A to C, it is entirely moving in the x direction and its magnitude is 40. So the displacement vector here is 40I. And what is the displacement vector AB? So you can see here the displacement is from point A to point B, and you can see in this Cartesian coordinate that the particle also move in the y direction. It is also moving in x direction and y direction. It is actually moving in the both direction, x and y. And what are the coordinates? So here the coordinate are 0 0. This is at origin A, and here the coordinate is 20 20, right? Because in the x direction we saw that this is 20 from A, so this is 20. So this coordinate is 20 0, right? Y is 0 here, but x is 20, and this is 20 20. This is 0 20. So particle moves from 0 0 to 20 20. So its displacement vector is 20I plus 20j. It's moving in positive 20 in the x direction and positive 20 in the y direction. So this is the position vector. Then my average velocity will be 40I minus 20I plus 20j divided by 2, and this is all the vector operations. So you can add or subtract the same component of vector, so it will become 20I plus 20, it become minus 20j divided by 2. So your average velocity vector will be 10I minus 10j. And if you want to find the magnitude of average velocity, it will be 10 square plus 10 square. Basically the component square of this vector, which is 100 plus 100 under root. So magnitude of average velocity will be root 200 meter per second. So this is the average velocity, and this is a vector average velocity, vector form of your average velocity. So we use the previous question concept to determine the position vector or displacement vector first. Once we got the displacement vector, we found the average velocity. But we use a little trick here as well, we write the because we need to find the velocity average velocity when it moves from point B to point C, and we define the position vector as position. So this is basically a position vector BC, and we define in terms of AC minus AB, right? Because we have already given time when it moves along AC and moves along AB. When it is moving from A to C, it is 3 second. It takes 3 seconds, and when it is moving from A to B, it is taking 1 second. So the remaining time it should spend between B and C. So the position vector here is RAC minus RAB. So you need to find what is RAC, what is position vector at AC, and what is position vector at AB. And you can see that first, while moving from A to C, it is moving only in the x direction, and the magnitude is 40 meter. It is covering the 40-meter distance. So the vector is 40i. But when it moves from A to B, it is also moving in the y direction. So it is moving in x and y both direction. And from the magnitude analysis, it is moving from 00 to 2020, which means 20 in the x direction and 20 in the j direction. So the vector displacement vector is 20i plus 20j. So when you substitute in this expression, you will get the velocity, average velocity vector, where the particle is moving B to C, which is tan I minus tan j. And the magnitude, for the magnitude, you can use this relation that we have used in the multiple previous question now, which are come out to be root 20 meter per second. So until now we have looked problems which are based on the Cartesian coordinate. But now we will solve few problems which are based on curvilinear or polar coordinates. So in the polar coordinate, or in the curvilinear coordinate first, we define the velocity vector in tangential and in normal direction. Right, so my velocity in just a second. Yeah, so my velocity can be given as along the tangential direction like this, and the magnitude is r theta dot in the tangential direction, and my acceleration vector can be given as this is in the tangential direction. So basically this in the tangential direction. So here you can see the e to the power t, which is the basis of the coordinate system, is also get changing. And for e to the power e dot t, which is dEt by dt, can be defined by the normal basis vector, and the acceleration vector in this coordinate you can have v squared by r in the normal direction and v dot in the tangential direction. So this is your acceleration vector. So here I am talking about the curvilinear coordinate. So if this is my point, this is my velocity vector in the tangential direction, which is tangential direction means the tangent to this curve, and this is the normal direction. This is the tangential direction, and along the tangential direction I am defining my velocity vector, but the acceleration has two components, one along the normal direction and one along the tangential direction. So we will be using this expression to find the variable. So we start with a very simple question. Determine the maximum constant speed a race car can have if the acceleration of the car cannot exceed 7.5 meter per second while rounding a track having a radius of curvature of 200 meter. So here in this question we have given that the determine the maximum constant speed a race car can have. So we have to determine the maximum speed and it is a constant, which means my velocity vector is a constant, it is not changing in the tangential direction. So this thing is a constant, it is not changing in the tangential direction, which means my tangential acceleration is zero. So basically this part of the acceleration is zero and only the non-zero acceleration part we have is the normal component of acceleration. So only this part is non-zero. So my normal component of acceleration is v squared by r, and the acceleration cannot be exceed 7.5. So it's 7.5 equals v squared, and the radius of curvature is 200 meter. So my v square is 7.5 multiplied by 200. So v is 38.72 meter per second. So it's a simple problem. So we have already been asked to find the maximum speed, and that maximum speed is constant, and we have given the acceleration. So since it's a constant speed, the velocity in the tangential direction should be a constant, it should not change, which means the acceleration in the tangential direction is zero, and we have only non-zero acceleration which is given, which should be in the normal direction, and it is 7.5 meter per second. So the acceleration in normal direction is v squared by r. So my v come out to be 38.72 if I use the expression. So let's move to the next question. So here we have given the truck travels in a circular path having a radius of 50 meter and at a speed of 4 meter per second. For a short distance x equals 0, its speed is increased by v dot 0.05 s meter per second square, where s is in meters. Determine its speed and magnitude of acceleration when it is moved s equals 10 meters. So we have given the v dot, which is 0.05 s, and you can see that this v dot is this tangential component of acceleration. So this v dot is basically the tangential component of acceleration, which can be defined by at, right? So we have given the v dot or the tangential component of acceleration, and we have been asked to find the speed and magnitude. So we will be using v dv equals at ds. In the beginning of this class, we actually integrate this expression from v1 to v2, and I am integrating from 0 to s equal 10 meter. So it will be v square by 2 from v1 to v2, and here at is v dot, which is 0.05 s. So it's 0 to 10, 0.05 s ds. So it will be 0.05 s squared by 2, 0 to 10, and this will be v2 square minus v1 square, and here I can multiply it by 2. So it will be 2 minus v1 square equals 2 0.05 100 by 2, and if you solve you will get v as 4.58 meter per second. Now we have already given the tangential component of acceleration. So to find the normal component of acceleration, we have the formula v squared by r, and r is 50 meter. It's the radius of curvature, right? And so it is 4.58 square by 50. So it's 0.419 meter per second. Similarly, AT is given by 0.05 s, and we need to find the magnitude of acceleration at 10 meter. So it is 0.05 multiplied 10, so it is 0.5 meter per second square. So my overall magnitude is AT square plus AN square. So basically 0.5 square plus 0.419 square. So your acceleration will be 0.642 meter per second. So it's a pretty straightforward problem because we have been given v dot, which is the tangential component of acceleration, and we have been asked to find the speed and magnitude of acceleration at s equal 10 meter. So we use the general formula here, and we integrate this formula to find the speed, which is 4.58 meter per second. Then to find the magnitude of total acceleration, we need the normal and tangential component of acceleration. So we have already given the tangential component of acceleration in terms of position. So we can easily find that it's 0.5 meter per second square, and the normal component can be easily found by this expression, and then we found the total acceleration. So this is a very similar problem. So here we have given the acceleration, which is a function of t. And we have been asked to determine the magnitude of velocity and acceleration here. So it says that if the car B turns such that its speed is increased by at 0.5 to the power et, if the car starts from rest when theta equals 0, determine the magnitude of its velocity and acceleration when t equal 2 seconds. So if car turns here, it possesses acceleration, which is the tangential component of acceleration, and this is the normal component of acceleration. So my tangential component is 0.5 e to the power t, and my normal component is unknown, which is v squared by r. So I can write the acceleration as change of velocity in time, which is change of velocity, which is 0.5. Sorry, this is the acceleration. So my velocity will be acceleration. I have to integrate this. So my acceleration can be written as 0.5 e to the power t. So basically I have to integrate 0.5 e to the power t, this expression. So I will get the velocity as 0.5 et minus 1. And I have to find the acceleration and unknown variable like velocity and acceleration at t equal 2 seconds. So v at t equal to will be 0.5 e to the power 2 minus 1. you solve this, you will get V as 3.195 meter per second. Now to find the acceleration, you have already given the tangential component of acceleration, and at time t equal to 2 seconds, your tangential acceleration will be 0.5 e to the power 2, right? To find the normal component, you will use this expression. So your V is 3.195, so it will be 3.195 square by R. R is 5 meter. So your normal component of acceleration is 2 meter per second square. And your tangential component of acceleration is 3.69 meter per second square. So your total acceleration will be at square plus am square. So it is 'So the acceleration magnitude will be 4.2 meter per second square. So here also you can see that we just use the expression here. It's nothing very complicated. We have identified that the acceleration was the tangential acceleration that we have given in the question, and we use the general formula here. Acceleration, tangential acceleration, which is the change in tangential velocity with time, to find the tangential velocity. So we already have the tangential acceleration. Then we found the normal acceleration to find the overall magnitude of acceleration. So most of the problem are like this only here. So that's it for today. So we actually started with the friction problem, then we solved the kinematics problem in the Cartesian coordinate system. We come to know the difference between the displacement and distance. Conceptually, that what is the basic mathematical difference between displacement vector, position vector, and the distance we identify from one problem, and then we solve one problem where we employ this concept. Then we solve a couple of problems based on the curvilinear motion or in the curvilinear coordinate system. First, we have defined the expression of acceleration like tangential acceleration and the normal acceleration expression. And we saw that in both questions, once we identify the component of acceleration, we can count the another component of acceleration because it has a fixed expressions here. Once you find out or figure out the component of acceleration in the tangential and in the normal direction, similarly the case with the velocity, you can actually find the total acceleration or the total velocity. So in the curvilinear coordinate, you only have this tangential component of velocity. And in the next class, we will solve a couple of problems from the polar coordinates where we actually define the component of velocity and acceleration in the polar coordinate in terms of r component and theta component, and we will solve the problem. So basically, the method will be the same. Only the expression of component of acceleration and component of velocity will be different a bit, but the concept will be the same. We need to figure out the component of velocity in the r and theta direction. Same with the acceleration, we need to figure out the component of acceleration in theta and r direction, and then we will find the total magnitude of it. So that's it for today. Thank you.